Welcome everyone. Today, we are beginning Chapter 12 on magnetism. This material is part of your SF0024 course on optics, modern physics, and electricity, prepared by Dr. Muhammad Izzuddin Rumaling, delivered to you by Dr. Jackson Chong. In this chapter, we will cover 5 main areas. First, we will look at the basic properties of magnets. Second, we will explore the magnetic field due to current. Third, we will calculate the magnetic force on a moving charged particle. Fourth, the magnetic force on a current-carrying conductor. And finally, we will study the torque on a coil. Let's start with the basics. Magnets can be divided into 2 primary types: permanent magnets and electromagnets. You've likely seen iron objects being strongly attracted to the ends of a magnet. These ends are what we call poles. Moving on to how magnets interact, we see that they exert either attractive or repulsive forces on one another. Simple experiments show that like poles repel while unlike poles attract. A critical property to remember is that there are no magnetic monopoles. Regardless of how many times you cut a magnet, every single piece will always retain both a north and a south pole. To quantify these effects, we define the magnetic field, denoted by the vector B, which has the SI unit of Tesla, T. The direction of the field at any point is defined as the direction in which the north pole of a compass needle points when placed there. While Tesla is the standard unit, the field is also occasionally measured in Gauss, G, where 1 Gauss is equal to 10 to the power of -4 Tesla. We visualize these fields using magnetic field lines, which follow 4 main rules. First, the lines never intersect one another. Second, they form closed loops that originate at the North Pole and terminate at the South Pole. Third, the lines are closer together at the poles, indicating a stronger field. Finally, if multiple fields are present, their lines can be superimposed to represent the resultant magnetic field. Earth itself acts like a massive magnet, which is why the magnet inside a compass seeks the geographic poles. The true source of Earth's magnetic field is the electric current flowing deep inside its core. Although the exact process is not yet fully understood, scientists believe this current is driven by the planet's rotation. Furthermore, convection currents within the hot liquid core also play a significant role in maintaining this field. Magnetism starts at the atomic level. Inside every atom, electrons have a property called spin. This spin makes each electron behave like a tiny magnet. In most materials, these tiny magnets point in different directions, so their effects cancel out. As a result, the material does not show magnetism. In some materials, such as iron, many electron spins point in the same direction. When this happens, their magnetic effects add together. This makes the material magnetic and strongly attracted to a magnet. This is why some materials are magnetic while others are not. Let's focus on ferromagnetic materials, such as iron, cobalt, and nickel. In these substances, a strong coupling occurs between neighboring atoms, causing them to form large groups where their spins are all aligned. These groups are known as magnetic domains. When there is no external magnetic field present, these domains are randomly oriented, pointing in various directions. However, when we apply a strong external magnetic field, more of these domains begin to align with that field. Because these domains align in the presence of a field, ferromagnetic materials become temporarily magnetized and are attracted to magnets. We categorize these materials as either hard or soft. Hard magnetic materials are those that retain their magnetism, meaning their domains stay aligned, even after the external field is removed. In contrast, soft magnetic materials easily become unmagnetized once the field is gone or if heat is applied. Soft materials are ideal for use as cores in electromagnets, as their domains align to significantly increase the overall strength of the magnet. Now, let's explore how electricity creates magnetism. As shown in these diagrams, when no current flows through a conductor, all nearby compasses point in the same direction, following Earth's magnetic field. However, as soon as current begins to flow, the compass needles deflect to point in a direction tangent to a circle around the wire. This observation proves that the magnetic field is produced directly by the current flowing through the conductor. To mathematically define this relationship between the magnetic field B and the current I, we use Ampere's law. If we imagine a closed path around the wire and divide it into small segments of length delta L, the law states that the sum of the products of the tangential magnetic field and each segment length equals the product of the current and a constant called mu. Using Ampere's law for a long, straight wire, we see that the magnetic field magnitude is constant at any point on a circular path of radius r. Since the total path length is simply the circumference of the circle, 2 pi r, we derive the formula B equals mu I over 2 pi r. To find the field's orientation, we use the right-hand grip rule. Point your thumb in the current's direction, and your fingers will curl in the direction of the magnetic field lines. Let's apply our straight wire formula with example 1. Imagine a long, straight wire carrying a current of 5.00 amperes. We want to find the magnetic field at the location of a proton situated 4.00 millimeters away from that wire. By using the magnetic equation, and plugging in our known values, we calculate a magnetic field magnitude of 2.50 times 10⁻⁴ Tesla. To determine the direction, we apply the right-hand grip rule. At the position of the proton, the field is directed into the page. Now, it's time for you to try this yourself. Consider a power line positioned 60.0 meters above the ground, carrying a current of 900 amperes northward. Your task is to find the magnitude and direction of the magnetic field produced on the ground directly below. As a hint, you should treat the northward direction as being into the page. After applying the straight wire equation, you should find that the field magnitude is 3.00 by 10 to 6 Tesla and points toward the west. The strength of a magnetic field can be significantly enhanced by forming the wire into a loop. In this configuration, all of the segments of the loop contribute to a magnetic field pointing in the same direction at its center. We determine this direction using the right-hand grip rule, where your thumb represents the magnetic field B and the curl of your other fingers represents the current I for a circular loop of radius r with n turns. The field magnitude at the center is given by the formula B equals mu n L over 2 r. When a wire is bent into a coil of several closely spaced loops, it forms what we call a solenoid, often referred to as an electromagnet. Inside the solenoid, the magnetic field lines are parallel and closely spaced, resulting in a field that is strong and approximately uniform. Conversely, the field outside is non-uniform, weak, and directed opposite to the interior field. To determine the field's direction inside, use the right-hand grip rule. Point your thumb in the direction of the magnetic field, while your curled fingers follow the direction of the current through the loops. To calculate the magnitude of the magnetic field inside a solenoid, we apply Ampere's law to a rectangular path. Because only the interior segment of this path contributes to the calculation, we derive the formula B equals mu n I, where n represents the number of turns per unit length, n equals n over L. It is important to note a key variation. The magnetic field strength at the very ends of the solenoid is exactly halved, following the formula B equals mu n I over 2. Let's apply these concepts in example 2. We have a solenoid 10.0 centimeters long with 100 turns of wire, carrying a 0.500 ampere current. First, we convert the length to 0.100 meters to find, which gives us 1000 turns per meter. Plugging these into the solenoid formula results in a magnetic field magnitude of 6.28 times 10⁻⁴ Tesla. Now it's your turn to apply what you've learned with a practical design problem. Imagine we want to produce a magnetic field of Tesla along the axis of a long solenoid. The solenoid is 0.150 meters long, has a radius of 0.0500 meters, and features 20 turns per centimeter. Your task is to calculate two things. First, the amount of current required to produce this field, and second, the total length of wire needed to build the solenoid. Remember to convert those turns per centimeter into turns per meter before you begin your calculations. We are now moving on to the magnetic force on a moving charged particle. Experimental observations show two very important things. First, a stationary charged particle does not interact with a static magnetic field. The particle must be moving to experience a force. Second, this force reaches its maximum value when the particle moves perpendicularly to the magnetic field. We can summarize these rules with the equation F equals qv sin theta, where theta represents the angle between the particle's velocity v and the magnetic field B. To determine the direction of this magnetic force, we use Fleming's left-hand rule. Extend your left hand so that your thumb, index, and middle fingers are all perpendicular to each other. Your index finger points in the direction of the magnetic field, your middle finger points with the velocity of the particle, and your thumb will indicate the resulting force. While this rule is designed for positively charged particles, you can also use it for negative charges. Just remember to invert the result to find the true direction of the force. In example 3, you can use Fleming's left-hand rule to identify the direction of the magnetic force. For example, in Figure 1, the magnetic force is directed to the left. In Figure 2, the magnetic force is directed into the page. In Figure 3, the magnetic force is directed downward. In Figure 4, the magnetic force is directed out of the page. In example 4, we want to find the magnitude and direction of the magnetic force on the proton, which moves at 8.00 by 106 meters per second southward, and it enters a region in which there is a magnetic field of magnitude 2.50 t, directed eastward. Using the magnetic equation for a point charge, we determine the magnetic force F equals 3.2 by 10 to 12 Newton and its direction is upwards. Now, let's try this example yourself. You are given a long, straight wire carrying a current 5.0 amperes and a particle having charge of 1.60 times 10 to the minus 19 coulombs is traveling upwards with speed 1.50 times 10 to the 3 meters per second and having a magnetic field of 0.25 millitesla. Find the distance of the particle from the wire and the magnetic force exerted on the particle. Next, we examine the specific motion of a moving charged particle inside a magnetic field. When a particle moves in a direction perpendicular to the field, the constant magnetic force causes it to trace a circular path of radius. If the particle enters the field at an angle, its path becomes helical. Regardless of which trajectory it follows, Fleming's left-hand rule confirms that the magnetic force always points toward the center of that circular path. We now shift our focus to the magnetic force on a current-carrying conductor. Since electric current is essentially a collection of moving charged particles, these individual charges experience a force that is transferred to the wire. This interaction explains why we observe a wire deflect when current flows through it while inside a magnetic field. The total deflection of the wire is caused by the resultant magnetic force generated by the combined movement of all those individual particles. To quantify this effect, we recognize that each moving charged particle contributes to the total force exerted on the wire. By taking the force on a single particle and multiplying it by the total number of particles n, we can derive a macroscopic equation. After substituting n with the particle density and rearranging terms, we find that the expression for drift current, I equals NAQV, simplifies our equation to F equals ILBs in theta. You can determine the direction using Fleming's left-hand rule by replacing the velocity finger with the direction of the current. A key advantage here is that, unlike the case for single moving charges, the result is always consistent with the actual direction of the force. Let's apply these concepts in example 5, where a 16.0 cm current-carrying wire is positioned between the pole faces of a magnet. The wire carries a current of 2.40 amperes upward, and the magnetic field strength is 0.0720 Tesla pointing out of the page. By converting the length to 0.160 meters and plugging the values into our formula, we calculate a magnetic force of 0.0276 newtons. Using Fleming's left-hand rule or other appropriate methods, we can conclude that the direction of this force is rightward. For this, try it yourself exercise. Consider a conductor suspended by two flexible wires with a mass per unit length of 0.0400 kilograms per meter. Your goal is to determine the current magnitude and direction required for the tension in the supporting wires to be zero when subjected to a 3.60 Tesla magnetic field directed into the page. According to Newton's laws of motion, you must realize that the magnetic force must exactly counterbalance the weight of the conductor. By rearranging the force equation to solve for current while incorporating the mass per unit length ratio, you should calculate a required current of 0.109 amperes directed to the right. Next, we explore the magnetic force between two parallel conductors, which occurs when the magnetic field from one wire passes through a nearby second wire. By substituting the standard field formula for a straight wire into our magnetic force equation, we derive the force per unit length. This equation, L, F, equals 2 pi d mu o, I, 1, I, 2, shows that the force depends on the product of both currents and the perpendicular distance d between the wires. It is a fundamental principle that both parallel conductors exert a force of the same magnitude on each other. Whether they attract or repel depends on the direction of their currents. Wires carrying current in the same direction will attract because the resultant magnetic field between them is weak. On the other hand, wires with opposite current directions will repel each other because they create a strong resultant magnetic field in the space between the conductors. Let's apply this in example 6, where two parallel wires are separated by 6.00 centimeters, each carrying 3.00 amperes in the same direction. Using our formula, we find the magnitude of the force per unit length is 3.00 times 10 minus 5 N per meter, and because the currents are in the same direction, the force is attractive. To verify the attractive force, you may use Fleming's left-hand rule to identify the magnetic force for each wire. Try it yourself. Problem involving two wires where the upper wire levitates due to the magnetic force from the lower wire. In this case, since the force must oppose gravity, the currents must be flowing in opposite directions to create repulsion. Use the force per unit length equation, obtain the value for current, and the final answer is 7.07 amperes. We then shift to torque on a coil. When a rectangular loop of wire is placed in a magnetic field, the two segments perpendicular to the field experience forces acting in opposite directions, which create a torque causing the coil to rotate. This rotational torque only occurs when the coil is parallel to the magnetic field. If the coil is perpendicular, no torque is exerted. By summing the moments of the forces on the perpendicular segments, we can derive the maximum torque. For a single loop, this torque is the product of current, loop area, and field strength, and for a coil with n turns, the maximum torque is expressed as tau max equals NIAB. More generally, torque is expressed as ni absent theta, where theta is the angle between the magnetic field and the normal to the loop's surface. For a loop parallel to the field, this angle is 90 degrees. This is the fundamental principle behind electric motors, which contain a coil positioned between permanent magnets that rotates when current flows, converting electrical energy into kinetic energy. While torque is maximum when the coil is parallel to the field and zero when perpendicular, the coil continues rotating due to rotational inertia. To maintain continuous rotation in a DC motor, the current must be periodically reversed using split-ring commutators. Applying this theory in example 7, a 20-loop square coil with a 3.00 ampere current in an 8.00 Tesla field will experience a maximum torque of 4.80 Newton-meters. For our final try-it-yourself exercise, you are designing a 12.0-volt DC motor with a 50-turn circular coil. Given a target maximum torque of 5.00 times 10⁻³ Nm and a magnetic field of 0.500 Tesla, you must determine the required resistance. To solve this, you must calculate the area of the circular coil, apply the torque formula to find the necessary current, and finally use Ohm's law to find that the resistance should be 471 ohms. To wrap up Chapter 12, let's review our key formulas for magnetic fields. B. For a straight wire, B is μ I, 2 pi r. For a circular loop, B at the center is μ I, 2 r. And for a solenoid, B inside is μ Ni while it is halved at the solenoid's edge. Always remember to use the right-hand grip rule to determine the direction of these fields. Finally, we summarize the magnetic force cases. For a moving charged particle, the force is QV sin theta, and for a current-carrying conductor, it is IL sin theta, using Fleming's left-hand rule for both. For two parallel conductors, the force per unit length is μ I1, I2, 2 pi d, where like currents attract and unlike currents repel. Lastly, remember our maximum torque formula, NIAB. Thank you for following along with this chapter. Please remember to scan your attendance in the designated OB link shared in the ITEL Learning Management System.